Our universe is a busy, noisy place. Stars are born in violent nurseries of gas and dust. They die in cataclysmic explosions we call supernovae. Black holes shred entire star systems, their gravitational appetites never satisfied. Amidst this cosmic symphony of creation and destruction, we listen. We point our massive radio telescopes toward the heavens, straining to hear the faint whispers from across the cosmos. Recently, we heard something new, something strange. A signal arrived from the depths of space, a brief, powerful burst of energy that defies our simple explanations. It is a true cosmic mystery, and science loves a good mystery. This is the story of that signal, a puzzle sent across billions of light years just for us to find. This essay is your guide to this enigma. Discoveries in astronomy often happen not with a shout, but with a quiet flicker on a computer screen. This signal was no different. It was first found buried within vast archives of radio telescope data. In 2007, an archival search of Parkes telescope data, led by Duncan Lorimer, flagged one incredibly bright, astonishingly brief burst. It lasted less than 5 milliseconds. Many things can mimic a cosmic signal. Faulty equipment, even a microwave oven. Scientists ran rigorous checks. They confirmed it was not a hardware glitch, and not terrestrial interference. The crucial evidence was dispersion. Radio waves traveling through intergalactic plasma arrive earlier at high frequencies than at low. This signal showed a massive dispersion delay, far beyond anything in the Milky Way, implying an origin very, very far away. That first event, the Lorimer burst, became the prototype for fast radio bursts, FRBs. As other telescopes looked, more appeared. The community slowly confirmed a genuine, baffling feature of the universe. To hear these faint whispers from across the universe, you need a very big ear. Radio telescopes. Single colossal dishes like Parkes and the former Arecibo collect more waves and detect fainter signals. They were crucial in the early days, spotting fleeting events. Then came interferometers, many smaller dishes acting together for sharper images. CHIME scans a huge swath of sky every day, becoming an FRB finding machine. The Very Large Array links 27 dishes to pinpoint locations with remarkable precision. Instruments record flux density in Janskys, timing across frequency to get dispersion measure and distance. They capture polarization, twisted by magnetic fields along the line of sight, clues to the journey. Next comes the SKA, orders of magnitude more powerful, detecting thousands to millions of FRBs, enabling population studies and cosmic web probes. From curiosities to demographics, categorize, trace origins, and use them as tools. When we look at these signals, we see graphs, time in milliseconds, frequency in radio bands, a short, sharp spike, then a downward sweep, dispersion, highs first, lows milliseconds later, proof of travel through intergalactic plasma, physics in action. An FRB lasts mere milliseconds yet can release a day to a month of the sun's energy, from billions of light years away. Unlike broad noisy spectra, many FRBs sing a single clear narrow band note, suggesting coherent emission. Some are one-offs, others repeat, letting us study them up close. FRB 121102 has flashed hundreds of times with complex substructures, implying a long-lived variable central engine. The first rule of science: doubt everything, especially your own findings. Primary suspect, RFI. Our planet is awash in radio. Cell phones, satellites, GPS, Wi-Fi, even appliances. If two distant telescopes see it simultaneously from the same sky position, it is almost certainly not local. Next, dispersion measure. DM counts free electrons along the path. Above Milky Way expectations means intergalactic origin. We chase counterparts in visible, infrared, X-ray, and gamma ray. A Rosetta Stone if timed with the radio burst. Most searches come up empty, radio bright, otherwise quiet. The mystery deepens. Repeaters let us localize to host galaxies, from dwarf star formers to spiral arms, even a globular cluster. Diversity implies multiple channels. Leading model, magnetars, neutron stars with magnetic fields 1,000 times stronger than typical. Crust cracks, field lines snap, energy erupts, a colossal, violent flash. In 2020, an FRB-like burst in our Milky Way was traced to a known magnetar with simultaneous X-ray and gamma-ray emission, a smoking gun. But the galactic event was thousands of times less energetic than distant FRBs. Some repeaters cycle, active weeks, silent months, hinting at orbital companions or periodic environments. Other candidates, neutron star mergers, ultra-young pulsars, or matter near supermassive black holes. Perhaps multiple FRB types. The universe is rarely simple, and it keeps surprising us. Inevitably, we ask, could it be them? Could it be a sign of extraterrestrial intelligence? As Carl Sagan said, extraordinary claims require extraordinary evidence. So far, we have none. SETI is legitimate science. FRB's narrowband spikes resemble power-efficient transmitters. Repeaters could be interpreted as beacons, saying, "We are here." But the energies are stellar scale, wasteful even for a Type II civilization. And the bursts lack data modulation. An artificial origin is a last resort. Occam's razor favors exotic stellar physics over galaxy-spanning aliens. For now, not proven. But the search continues. We keep looking. What is the central engine? Magnetars can make FRBs, but do they make all of them, especially the most energetic? How do some sources survive and burst hundreds of times? Is it a solitary compact object, or a complex binary, perhaps orbiting a black hole? How is energy converted so efficiently into coherent, narrow-band radio? Shockwaves in magnetized plasma? Relativistic particle beams? Details remain murky. DM totals electrons, but not their distribution. Are electrons mostly in cosmic voids, or in dense plasma near the source? Polarization and scintillation, the twinkling of radio, carry environmental clues, but disentangling them is hard. Do one-offs and repeaters come from different sources, cataclysmic versus long-lived, or do all FRBs repeat with long, quiet spells? Answering this demands patience and time. The universe speaks slowly. It is a long conversation. The deep space signal is not a story with an ending. It is an ongoing investigation. The next chapter belongs to more powerful, more sophisticated telescopes. CHIME will keep building a massive catalog of thousands of bursts, turning anecdotes into statistics. We will classify families, sort by properties, and map their spread across the cosmos. Rapid, multi-wavelength follow-up will link radio triggers to optical and high-energy telescopes in real time. The goal: catch the source in the act, a simultaneous flash that ties radio to the engine. The square-kilometer array will be a quantum leap, sensitivity and resolution far beyond today. It will detect fainter, more distant FRBs and routinely pinpoint host galaxies. Beyond discovery, the SKA will map cosmic magnetism and weigh the missing matter between galaxies using FRBs as probes. A 5-millisecond blip in an old dataset blossomed into one of modern astrophysics' most exciting frontiers. These signals are a gift, challenges that expand our understanding. The story is far from over. The only way to find what makes these strange sounds is to keep listening. So, let us keep our ears open, our minds curious, and our eyes on the data. The universe is speaking, and we are learning its language. Keep watching the skies.